Okay, so I will talk a bit about a few statistical perspectives related to benchmarking in AI. So this is kind of like a sort of, in a way, a big topic. So several different things that we could discuss. I decided to kind of focus on one specific topic, which is related to how to kind of quantify uncertainty when doing benchmarking. And I will focus on kind of two different, let me see. Just one second. There we got it, yeah. So I will focus on kind of two different parts, the supervised learning part, but also a bit going into large language models and other models that kind of has a language output. I will also have one slide because I saw that I got 5 minutes more, so I added a slide on also a bit on benchmarking on LLM's ability to quantify uncertainty in the responses, which I will also say a few words about. Okay, but let's start with more like the traditional machine learning thing, which I think also is good in the context of LLMs to have this as sort of like a background. So in kind of like the traditional machine learning and then evaluating, typically our benchmark data set is divided into different parts. For example, a training set, a validation set, and test set. And often this is also as part of the benchmark data set, there's also given as part of it, so it's kind of restricted that you should use this for training, this for the validation, and this for test, for example, maybe to make the comparison easier. But this can also introduce some biases, because if you kind of reshuffle this, then you will probably get different results and also potentially different rankings. And it is also common to evaluate using cross-validation, because then all the different data points can be used for evaluation, so this can potentially reduce, or usually reduce the uncertainty in the benchmarking result. So let's just reflect a bit on different kind of sources of uncertainty when we do benchmarking in this kind of context. The first one here on kind of like the final sample. So this is the one that is kind of like the most common from the statistical point of view, that when we have a benchmark data set, we can imagine that these are sort of like samples from a larger population, and we create our data set. But since we have a limited number of test examples or examples in our data set, this will introduce uncertainty. Another one is that also the performance, as I briefly mentioned, it also depends on how are the different data points distributed between the training set, validation set, and test set. If this is kind of organized in another way, we will obtain slightly different results. And also, this is the same if we use cross-validation for evaluation. This also affects how our results, if we kind of permute or redistribute which data points that are parts of the different folds. And it's quite complicated, because these different parts here, the training part, the validation part, and the test part, kind of contributes to the uncertainty in different ways. So the test is kind of like the average, but also the training of the model. So if you train the model, you kind of get uncertainties in the weights in your trained model. If you had other data points in your training set, you will get other weights. So these different parts contribute to the uncertainty in different ways. And another example is also that in these kind of training algorithms, there are also some sort of like randomness. For example, you could have like a random initialization of the algorithm. So if you train the algorithm 2 times, you doesn't necessarily get exactly the same model. And for example, also in random forest, you have kind of like the bootstrap component. So these are examples of different sources that contribute to uncertainty when you evaluate your model. So you get your result and you're happy with it, but there are also some different kind of sources to uncertainty. Okay, so let's have a slide on, well, in this context, how do we then try to kind of quantify uncertainty in our measured performance. And here I focus on cross-validation, but there are many of the same issues if you kind of focus on the more traditional division in training, validation, and test set. And for cross-validation, the one fundamental issue here is that when we look at this, the different training points can be used in different of these folds. So this data point here is used to train this model when it's tested here, but the same data point is also used for these test examples here. So this introduces some dependencies between the test results, which increases the variance. And it turns out that trying to precisely estimate what this variance is turns out to be very difficult. It's no unbiased estimate actually exists to estimate this variance. So that's kind of like a challenge. But there are luckily several different both statistical tests, but also different simulation procedures that take into account these additional dependencies and additional variance so that we can get some sort of, as best as possible, estimate of the performance in addition to some sort of uncertainty bound on it. And I can briefly mention one example. For example, here are a couple of packages, which is quite nice from Python, and one example here is one example of a method. So then we can imagine that we have some sort of performance on the original data set, but if we now do a performance on the Bootstrap data set, like over here, since some of the data points in the Bootstrap data set are kind of represented more than one time, that's just part of the characteristics of a Bootstrap data set, then when we evaluate the performance on this, usually we get a better performance. So in this example here, we get less error. So the error on, let's say, 1,000 Bootstrap samples could look like this, while on the original performance is over here. So we see that there's some sort of bias that is introduced here. So this kind of idea, the idea is that you can use these techniques to kind of try to bias correct. And there are different ways that this is done, basically. So that's just some thoughts on uncertainty related to more like traditional benchmarks. So let's move to large language models and also other models that can have language as output, natural language as output. So when we look at benchmarks on the internet and also in other contexts, usually no error bars are included as sort of the performance here. So this is just one example. So in some contexts, it could be useful if we could add some sort of error bars like this here. And often when error bars are added, this could also kind of change the view on how we look at this, because we see that, okay, with these error bars, maybe it's not that much of a difference between these methods that we first got the impression without error bars. I don't say that these error bars are realistic or not for this specific example. It's just for illustration. But still, it gives some idea that sometimes these error bars can change the view of our results. So when it comes to benchmarking for LLMs, for example, compared to the traditional setting, usually the models are pre-trained. So then the benchmark is only used for sort of like the testing part. And that's kind of like good news, because then several of these sources of uncertainty and these tricky dependencies that we discussed in the previous slides, we don't need to be concerned with this when it comes to LLMs. So then when computing uncertainty, we can, at least as a starting point, rely on traditional statistical approaches like confidence intervals and so on. So we compute the average score on our different test examples, different test questions, and we can compute confidence intervals or other measurements that we are interested in. Or for a bit more complex or for nonlinear metrics, like F1 score, for example, we can also just bootstrap our test scores. So it's, in a way, from a statistical point of view, fairly straightforward. Of course, often when in these benchmarks, there are often a lot of dependencies, because you can have, for example, a bunch of different questions for one specific document. So of course, these different dependencies also you need to take into account when you measure this. But usually it's fairly straightforward from a statistical point of view. But of course, there are a bunch of other issues with benchmarking that both Mikael and also Vlad discussed. So what I'm discussing here is like one piece of this puzzle, right? So you have all sorts of other issues related to benchmarking. This is the one that has to do with quantifying uncertainty. And some other kind of things on how to kind of do this. This is a paper that has some interesting discussions on this. Okay, there are a few formulas here, but it still should be fairly straightforward, I think. So here is a bit on, maybe just a couple of thoughts on when we want to quantify the uncertainty, are there any ways we can reduce our uncertainty estimate from a large language model point of view? So if we start like from the traditional statistical point of view, imagine that we have all these possible test questions that we could have for a specific task. We want to test for something, coding or math or whatever it is. And then we do some sort of random samples. We select kind of n tests from this. And then the average score here, that's basically our measurement of performance. So this is basically the height of these bars here, right? That's the average performance. And then we are interested in kind of computing the variance of this, which will then represent basically, you can say, the width of these bars. That's kind of like what drives how wide the error is. And sort of like a simple model for this, which I think is fairly representative, is that one important part is, of course, how many questions do we have in our test. So if our test consists of hundreds of thousands of questions, we don't need to be concerned about this uncertainty because it's so large so that this variance basically becomes very small. But if we have smaller, more specialized tests where the number of questions is a bit less, then this is something to keep in mind. And then we can think of two different sources of uncertainty in this variance. One is that from the benchmark, we have different questions that have a different difficulty level. So this introduces one sort of variance. So it's basically this uncertainty that we draw some of these questions from this population. So this is the one that is kind of like the traditional one from a statistical point of view. The other one is kind of like the generative part of the LLMs. So when you ask the LLM, you get an answer. But if you ask the LLM one more time, you get another answer. So this kind of uncertainty, that is also the generative part of the LLM. So this is kind of like maybe a good thing to keep in mind when we think about the uncertainty. And then just a couple of reflections on, are there any way that we now can reduce the uncertainty? Because we would like, of course, to have the performance, but we would like to have it as precise as possible to reduce the uncertainty. And then one thing that we could do is that we are not just generating one response, but we can generate multiple responses from the LLM. And if we do this, let's say we have the computational resources to, for every benchmark question, generate, let's say, k different responses, then our uncertainty will be reduced to this. So this one that is kind of like from the benchmark, we cannot really do anything about that one, or this one. But this one, we can at least reduce. And then, of course, then it's a bit about what kind of computational resources do we have. It depends on how many models do we want to compare and other considerations. But one thing that we could, for example, be one strategy is that, okay, this one we can reduce, so we should at least run this, generate a number of responses so that this part here is less than the one that we really cannot do much about. But of course, how do we determine such a K? This is from this paper. I didn't really see any way to do that. Maybe it's possible to do some sort of small pilot or something like that. But that's something to bit of an open question. Another part here is to basically, if we can get access to the token probabilities, and we have like questions where it's just basically one probability. Then basically these token probabilities can give us sort of like the expected answer, expected score we will get here if we kind of generated, let's say, infinitely many responses from the model. So if we can get access to the token probabilities in some simple cases, we can just, we'll be able to get this part of the uncertainty to vanish so that we only get this part, sort of like the benchmark part of the uncertainty left. Okay, so just one quick slide finally. I squeezed in this one since I saw I got a few minutes extra. Let's see if I get time after all. So when it comes to LLMs, we would like them to come up with some sort of response. We would also like them to have some sort of assessment of their uncertainty. So with the hallucinations and all this kind of stuff. So then we would like to quantify the LLM's ability to quantify this uncertainty. Quantify uncertainty, how reliable is it? And there are some examples from the literature. For example, I saw this paper here. They use sort of like some sort of score for how certain the model is, and let's see how this sort of like correlates with the performance of the model. Because if the model is very uncertain, we would expect poorer score, for example, poorer performance. And also in this paper here, they use conformal predictions. So they kind of have a smaller set. And then they suggest this metric where they kind of have accuracy divided by the size of the set. So if they kind of have a small set, you get a better score because then you have a smaller, let's say, think of confidence interval if you are not familiar with conformal prediction. But both of these metrics can be a bit risky to sort of develop your own metrics without any more like strong theoretical foundations. Because, well, okay, it looks intuitively appealing, but maybe still it can be quite risky. For example, for this one, it would be tempting to just try to include all possible answers in the multiple choice, for example, in the set, so that you are ensured the accuracy is equal to 1. So will anyone beat that one, for example? So if using metrics for these kind of experiments, I think it would be good to use established metrics, like, for example, this ECE or proper scoring rules from statistics, for example, which are founded more theoretically. Okay, so finally some conclusions. So there are methods to quantify uncertainty in benchmarks, but as we saw for more traditional supervised learning, there are several challenges with several sources of uncertainty and also some complex dependencies that make this actually quite difficult in many situations. And also for LLMs, there are several issues when it comes to benchmarking that I haven't discussed that much, but rather than especially Mikael discussed. But still, I think uncertainty benchmark could usually be reported more frequently and probably more reliable and what has been done. So, thank you.
Yes, thank you. We have time for one question. Yes, Michael.
Thank you. That was really great. So one question, why do people not do it, do you think?
Yeah, that's a good question. Probably they are not aware that it can be useful and important to do it. So maybe the main focus is not just getting the scores, and maybe they're not aware that it should be done to get a better overview. Would be my best guess.